So my idea is if you had a proton and an electron and you put the electron into the proton on the inside, that there was an orbital, then it would spin around in that shell and form a particle that has a charge distribution that has positive and negative parts. You could then stick another proton onto that charge distribution at the negative parts. So put a proton on there. There you go. There you go. Now you've got deuterium. That's my idea of what deuterium looks like. So let's do some math. Okay, mass balance first. So first of all, is the mass of the neutron greater than the mass of the proton plus the mass of the electron? Yes, that's true. Plus a little additional extra, which we're going to leave out for now. Then what about free neutron decay? In free neutron decay, right, a neutron that's flying through space without any attachments will break up into a proton and an electron, which is, there you go, spontaneously about every 10 minutes. What about neutron charge density? Studies lately have shown that the neutron charge density is not neutral, but goes positive and negative. This is the key, because if that's true, then maybe there can be an inner orbital. So what would this look like? Well, we know that in a regular charge that the force outside corresponds to something 1 over the radius away from the center of the charge. However, in a uniformly charged sphere, the interior forces go more as a linear k of the radius. If you use that formulation for the force inside the proton, then you can calculate a wavelength. You're going to do that? Okay. And you can calculate a wavelength for the electron, right? So remember, the electron wavelength momentum is h, is fixed, is a constant. So then if you substitute that in, you get a wavelength that's proportional to 1 over r, if you substitute that into the force equation. So this line represents the circumference of the orbital at that point. And you can see then, and then a line that represents 1 over r. And you can see there's a point where you could have a standing wave or an inner orbital. All right. What's the mechanism then of beta decay? Beta decay is that where the neutron breaks apart again into a proton and an electron. So I'm drawing a little, there's my little electron wave here inside the proton. It's not particularly representative, but what you need to see is that on the outside there are tunneling tails. This is quantum mechanical tails that extend beyond and outside the, we'll call it the capture radius. So how would this work? Well, basically, let's draw that quantum 101 quantum well here. And in the quantum well, we'll put our electron. And if I can find my pen, there we go. All right. So here's the sort of an electron, and I'm going to put some tunneling tails on there. It's a terrible, terrible diagram. You'll be punished later for that, I'm sure. All right, now we have our tunneling tails. So what can we assume that the electron will do? Well, we'll call it a beta pop. So inside, every once in a while, our little electron goes back and forth, but sometimes it just ends up tunneled to the outside. In that case, it's carrying a great deal of energy suddenly and instantaneously, and that causes a little bit of a pop. But the electron is out, and we have our beta decay. Pop. All right. It also pushes the neutron or the proton back the other way. Neutron stability. So what causes stability? Well, let's go back to our tunneling, and we're going to try and figure out, because something like deuterium does not decay, right? A lone electron will decay, but deuterium does not. So what would stability look like? It would look like, that's how you spell it. But from a quantum mechanical perspective, what does stability look like? Well, the idea here is that when you put the other proton next to, it extends the quantum well, the dimensions of the quantum well. And so now it's wider by drawing the electron towards the other proton. It then becomes more locked in because the wavelength fits better inside. Thus the tunneling tail's almost eliminated completely. Or completely as stability. Or it becomes so small that it goes to the ends of the universe. All right, so let's talk about the electric multipole properties of the neutron. Now suppose we have our neutron, right? If the charge density of the positive can be collected and set to be in the center, right, of a uniformly charged sphere, but yet our electron does not occupy the center, then we'll get an electric multipole, because the majority of the charge on the electron's time is spent away from the center. So now you have a electrostatic multipole. So what can multipole do? Well, multipole bonding would be, you have your proton with your electron in it, going around making this little kind of child's ball, little Pixar ball maybe, a little child's ball. And then your proton sticks to that, forming sort of a unit. Now you could stick another proton on there, right? But so that's deuterium. You can stick another proton on there, and you'll get tritium. Let me see. There we go. That's what the model looks like in 3 dimensions. Tritium. Let's talk about tritium. So tritium is 2 neutrons put together with 1 proton in the center. Yeah, that's not very good, but so tritium is not stable. Tritium decays via an electron emission to helium-3. So how does that work? So one of the electrons tunnels into the central proton. Now, it doesn't immediately kick out its neighbor, but eventually that kind of uncomfortable neighbor will kick out the electron, and then you've got one neutron in the center and two protons on the outside, and now you have helium-3. Helium-3. And that's how tritium turns to helium-3. So what's the proof of this? I mean, this is a lot of jaw music so far. Well, here's the decay issue. If you write down the mass of tritium, and need that eraser. All right. You write down the mass of tritium. Three 0.0160. Pay attention to that one. 4. That's like AMU. And then you write down the mass of helium-3. All right. All right. A little clearer here. 3 helium is 3.01602. 29, so I'll make it a 3. Alright, now the real issue is what's the mass of the electron that's emitted in the transition between the two. And in this case, the electron is right up here. The mass of the electron in AMU is 0.0005. Alright, here's the problem. There's not 5 in there. There's not enough mass to cover the electron, and that is an issue. So, what is the issue? Not enough. Not enough mass. Alright, so what's going on? Well, my idea is this. The tritium forms a strong N-pole of some kind. So here we draw the three of them. 1, 2, 3. And we put electron orbitals in those, which will make an electric multipole like this. And then the center protonic charges are like this. So you have positives and negatives separated by distance, which is the definition of a multipole. So, if this tritium multipole has properties, multipoles have properties, and one of the properties is that in a particular kind of electric field, the multipole will experience a force, either a rotational force to try and align or anti-align it with the field, or if the field is changing, the multipole can experience a actual translational force. And this is where I think the problem lies. I think the tritium number is wrong. And I think it's wrong because charges and mass, the mass of these nuclei is measured using a charge to mass ratio, which means that you have to apply an electric field and then measure how far the charge curves in response to the force that it would be experiencing in that field. So it will then curve, and you have you can calculate the mass based upon a charge to mass ratio, because the point at which it hits will be different depending on the mass of the. But if you have a multipole experiencing, let me draw it, because it needs to align with the field. Hold on. Right. No, wait, that's not aligned. That's anti-aligned. I need to turn it. Hold on. Turn it. Meep, 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 meep. Meep, 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 meep. Now imagine that that is in the field and is experiencing a force of translation. It will land somewhere else, giving you a different charge to mass ratio. But if you assume that it's not, then that's going to cause a measurement error. See, if you use the same mass and a different charge, a charge prime. All right, so here's a summary. I have a proton and I have an electron. If I could put the electron in the proton and spin it in an orbit inside, then I would get a particle that has a charge distribution like this, with negative and positive parts. I can use this, right? It's neutral far away, but attractive close. So I can use it to stick a proton on it. Not only that, I could stick another proton, or another neutron, excuse me, on the other side. And now I've got tritium. Now, if tritium has a negative, positive, negative, then it's a multipole. And if it's subjected to an electric field of the right type, it will translate. Now, the numbers for the mass of tritium are hinky, because the mass of tritium and the mass of helium-3, which is the opposite, 2 protons and a neutron in the center, are too close together to account for the electron that comes off when tritium decays to helium-3. So, the idea is that this multipole is experiencing translational force while we're measuring its charge to mass ratio, causing it to be off. So those numbers aren't correct for the mass of tritium. That's the gist of this part. In the next part, I want to show how you can use these to form nuclei. So this would be the structure of beryllium, except one little detail, there are these places in the center where you can pop another neutron, called a Lagrange point, but it is basically stable isotope, stable isotope. That is the key. So, next video!